Good morning, good afternoon, and good evening, ladies and gentlemen. Welcome to Yokogawa's webinar titled Isolation and High Voltage Measurements Using Data Acquisition. I would like to thank you all for taking the time to attend this seminar, and I hope you find it both helpful and informative. Before we begin, I would like to go over just a few housekeeping issues. The audio part of this seminar can be accessed either through the teleconference number provided in the Info tab of your WebEx Manager window or through the PC's speakers. To hear the audio through your PC, select the Communicate tab and join the audio broadcast. This seminar will last approximately 1 hour. Towards the end of the presentation, we will have the Q&A section where, time permitting, our featured speaker, William Chen, will answer some of the questions received from our audience. If your question is not answered during the presentation, please be assured that we will answer them all via email. All questions should be submitted in the Q&A windows or the chat window located in our lower right-hand corner of your screen. Our featured presenter for this event is William Chen, Product Manager with Yokogawa. William is responsible for the high-frequency instruments and high-speed data acquisition product lines. He has over 3 years' experience with Yokogawa as an applications engineer, supporting the Yokogawa Test&Measurement products. He has consulted on numerous products in multiple industries, including renewable energy, power electronics, motors and drives, automotive transportation, aerospace, and more. William has a degree in electrical engineering from Georgia Institute of Technology. Without further ado, I'll now hand it over to William.
Thank you, Christina, for the wonderful introductions, and welcome everyone to our Webinar Wednesday series. Today our topic will be isolation and high voltage measurements as it pertains to data acquisition. So there are a couple of several different topics that we want to be going over today. The very first one obviously is to go over basic considerations when making high voltage measurements. We'll also be taking a look at why do we need voltage isolation or isolation in general, and what are some of the benefits that isolation can provide for both your measurement system as well as your measurements themselves. Then we'll be taking a look at some common isolation types and how they're used, both internal and external isolation types. We'll be taking a look at some of the issues that non-isolated instruments present, such as common mode noise and ground loops, and how these isolation topologies will be able to solve these issues. We'll also be taking a look at how to reduce the signal noise in your measurements when making non-isolated and isolated measurements, and as well as what are the probing and signal conditioning considerations that you should take. And finally, we'll end off with going over some common data acquisition isolation architectures in today's technologies. So to get started, we first need to understand what is high voltage and what are the basic considerations that we should take when making these measurements. Now, the specific value for high voltage can change depending on the application that you're performing as well as the given standard. For example, IEC 60038 defines high voltage as any voltage greater than 1,000 volts RMS. Now, this is obviously going to be different, for example, from the ANSI C84.1 definition, which states that high voltage is anywhere between 69 kilovolt to 230 kilovolt. So different discrepancies, but as far as the basic considerations, regardless of the voltage value, the first concern I'm sure most of all of us have when dealing with high voltage is the risk of electric shock. Now, in most cases, direct contact with voltages greater than 42 volts will result in bodily harm. So for the sake of today's conversation, we will specify or define high voltage as anything greater than 42 volts. And really, some of the data acquisition, non-isolated data acquisition will see equipment damage at any voltage direct at 50 volts or higher. The risk of direct contact can be a result of improper grounding or improper wiring or using non-insulated or incorrectly specified connectors and cables. Now, to put this into perspective, the Center of Disease Control's National Institute of Occupational Safety and Hazard Organization reported that, on a yearly basis, there are over 10,000 injuries and 600 fatalities each year due to electrical hazards. So, as we can see, in fact, electrical accidents rank 6th among all causes of work-related deaths in the United States. So please don't be like our friend that you see here in this picture. Be aware of all safety warnings and take care to have documented safe working procedures in place when you are working with high voltages. Now, our next consideration when working with high voltage is the risk of damaging equipment. This includes equipment under the test, so this is your powered device. It can also include the measuring instrument itself, as well as any other connected device to either the measuring instrument or the device under test. So this can include, your laptop computers, your workstations, any monitors, video screens that you have going, or any test stands. And really, equipment damage can also occur when you have high energy transients. These transients come from lightning strikes, power outages, short circuits that we've made, or even power line malfunctions from the power company. Although uncommon, these transients from these situations can occur, and they do cause equipment failures that end up costing not only time, but a considerable amount of money to fix. And for sensitive electronics, it doesn't take much transient energy to really damage the internal circuitry. So you can see in the two example pictures that I have there, I'm sure this is something we've all experienced, throughout our electrical engineering career, whether we've burned an internal circuit board or whether it is a circuit breaker box that has actually caught on fire. These are all considerations that you should take when dealing with high voltages. Now, a third consideration or third concern that we need to take care of is ground loops. And ground loops are really the most common noise problems as well as issue when dealing with high voltage measurements. Especially in large-scale electrical systems, ground loops can really stem from poor grounding practices. As a simple example, in plumbing, you sometimes hear of hot water coming out of cold water faucets, even though there's not supposed to be a connection there. But somewhere in the water pipe connection, there was a common point where a crossover happened. And this same surprising result can happen in an electrical circuit where an unintentional ground is introduced at some point in the measuring system. It's not supposed to happen, but a common point to ground was introduced, and this creates a ground loop. So as you can see there, we have our instrument connected to the device under test, and we're using just a simple passive voltage probe, and we're connecting to multiple ground points. We have the ground point connected to the circuit ground as well as the receptacle ground that you see there. And when you create all these ground points, you're going to have a ground loop issue, which is going to cause some noise problems, but also it's going to impact your equipment. It may damage the equipment depending on how much current or how much voltage is circulating in that ground loop. So this is a problem that we'll take a look into deeply later on in this webinar, and we'll be showing you some ways of how you can resolve these ground loops. Okay. Now, another concern that's not fairly common that we don't always immediately think of, but unwanted noise. And I've listed on there, all these noise that we can typically see in our measuring instruments. So this includes not only common mode noise, but also your normal mode noise, As far as temperature data acquisition is concerned, you can have crosstalk, maybe some power line, 60 hertz humming or ringing as we like to call it. There's also, electrostatic and electromagnetic noise that can occur when you are dealing with industrial type environments. So we'll be taking a look at how isolation can be used to not only measure these problems, but also get rid of them as well. So since today's webinar obviously is the topic of isolation and data acquisition, it makes sense that we need to have an understanding of what isolation is. And to put it simply, isolation is separating two or more parts of a circuit or electrical system by physical or electrical barrier. In its simplest terms, isolation interrupts the current flow between the different potentials in the ground system. So isolation can really mitigate a lot of the problems that we just talked about and we presented at the beginning of this slide, which was ground loops, unwanted noise, risk of electric potential. These are all different things that, there are a number of specific isolation devices that you can implement both into your internal system design as well as external isolation devices to really mitigate these problems. And as you can see there on the left, I've given you some examples where your source is physically and electrically isolated from the receiver. And for internal isolation, this can include optocouplers or optical isolation. This can be analog or digital isolators. That can also include differential capacitor isolators as well. And not only these internal devices, but, we're also interested in external isolation devices and how they can be used when, say, for example, you can't modify a system already. Let's say you have an industrial motor or generator, and you're trying to find some way to eliminate the ground loops and the noise problems, but you're not able to physically insert these devices into the motors and drives. We have also external isolation devices that can help solve these problems. So obviously there are a lot of different situations where we can utilize the benefits of isolation, and what I want to do next is to identify these situations. And if you ever find yourself in one of these situations, you should definitely think about isolation as a means to solve the issue. So our very first case that we need to consider isolation is obviously when there's direct exposure or if you're within close working vicinity to hazardous voltages. So for industrial environments, this is fairly common. If you're working with exposed wiring or if you're connecting systems with metal contacts, such as BNC connectors or BNC alligator clips, or if you are working with potential transformers, current transformers, or any shunts that really deal with or have these metal contacts, you should consider isolation as a means to protect not only the user, but also the surrounding equipment from potential hazardous voltages such as arcing, for example. So as a general rule of thumb, you want to make sure that you perform all connections with all the devices disconnected from the mains. So this means whether this is a motor under test or if this is an entire test system, you want to make sure that it's not connected to the line power. And once you have done that, then you can make all the physical connections and wiring that you need to before you begin measurements. But let's say, you're not able to disconnect from the mains. There are also some simple benefits to using isolation in the sense that you can have the devices powered off and there can be energy running through the systems, but isolation will protect you as a user when you're directly connecting to these exposed wires. So our next situation, obviously, if you're working in an industrial environment where transient signals are common, these are common events or maybe uncommon events, but if there's a potential for, those lightning strikes or those short circuits, if you need to implement circuit breakers into your system, you should also consider external isolation as a means or a solution to preventing damage from your equipment. And the external isolation will also protect your data acquisition system from being damaged, as well as ensuring that the measurements you make are correct and not offset by some voltage. The next case we can take a look at, if you are dealing with noisy environments, or if you are making measurements and you're experiencing a lot of common mode noise, as we like to call it, or fluctuating ground potentials. Let's say, for example, you're not able to eliminate the ground loop from your system, but you still want to make accurate measurements without the influence of the ground loop noise or effects. There is external and internal isolation that can be used in these situations. This makes sense for large industrial plants or for enclosures that are built, already pre-built, and you're not able to go in and modify any of the equipment, or if it's not cost effective, then you should look at how isolation can be used and placed in between not only the device and the measuring instrument, but potentially also between the device and the power line to eliminate the ground loop. And really, the noise can be separated into two different categories, which we will take a look later. You have your normal mode noise as well as your common mode noise. And, you could be dealing with one or both. So we'll be taking a look at how to solve these issues later on in the webinar. As I've mentioned earlier, the next case is if you are in a electrically noisy environment. So let's say you are working with motors, generators, you're working with multi-channel temperature measurement systems, and crosstalk is an issue, or the fairly common power line noise. If you ever find yourself in these situations, the good news is isolation can help you to get accurate measurements, and the power line noise can not only be conducted through the data acquisition device itself or the power supply, but it can be radiated through EMI, so these are internal and external sources. So this can be coming through the cabling, the connectors, and as you can see in the example, if you've never dealt with power line noise, what's going to look like are these oscillations on your clean signal. So if you ever are dealing with oscillated noise on your system, then you should look and think about implementing isolation as a solution. All right, a couple more isolation cases. Let's say you need to measure low-level signal changes. So this could be a situation where you're working with shunts. For example, in that lower right corner picture, I have a system where we want to measure the voltage difference across a 50 millivolt shunt. But there's high common mode voltage, as you can see, between the circuit ground and the system ground. So there's 200 volts DC common mode voltage, and we only want to measure the 50 millivolt change. So how you're going to do this is through the use of isolation amplifiers, and we'll discuss a little bit more in detail how we can do that. As another example, if you're working with stacked voltage cell or battery cell testing, in these cases there can be common mode voltage between the battery cells, And let's say you want to measure or detect small voltage changes in between the cells. Well, the way you're going to do that, again, is by use of analog isolation amplifiers to really detect those small signal changes. Okay, one of the last cases, obviously preventing transient voltages from surging, throughout your measurement system. So transients affect a large amount of equipment, and this can include, as I've listed out here, pumps, inverters, motor controllers, various variable speed drives, compressors. So if you're working with any of these equipments, please be sure to think about using isolated data acquisition as well as external isolation to prevent these transient voltages from surging throughout your system and damaging everything. So next we want to go into detail, a little bit more detail about the issues that we presented earlier. And this was, as you can recall, ground loops, common mode voltages or noise, and how we can remove them by means of isolation. So ground loops are the most common noise problems in large-scale electrical systems, and as we mentioned earlier, they stem from poor grounding practices. A common misconception that beginning engineers have is that the earth ground at one location is going to be the same as the earth ground at a different location, but that's really not the case. Ground from the receptacle at different locations can have different voltage potential. This means that one could be sitting at 0 volts and the ground at another receptacle at a different location in the plant could be maybe 0.5 volts or even 1 volt. So there's a potential for voltage difference, and in this example that I've put here, let's say you have your data acquisition system connected to one receptacle in one room, and let's say you have a test environment in a separate room, and that's connected to a different power mains, okay? And let's say you're running cabling through the two systems. So this is communications cable or measurement cable. You want to make sure that you're not connecting the grounds internally between the two systems, because if you do that, you're going to create a ground loop. And what happens when you have a ground loop is, let's say, for example, the power shuts off or a lightning strike occurs, and you have these transient voltages that occur. Well, the transient voltage is going to cause that 1 voltage difference between the two receptacles. It may now jump up to several hundred or even several thousand volts across the instrument, and that's going to end up damaging both the instrument as well as the test cell environment. So if you have instrumentation grounded in different locations throughout your facility where different ground potentials do exist, you could very well experience a ground loop if the instrument itself is not isolated, or if the device under test is not isolated from the power mains. So let's take a look at 3 common ways ground loops can cause equipment problems. The very first problem occurs when power measurements are made on data acquisition, and you have low currents circulating through the ground loop. This will generate a oscillating or noise voltage that occurs as we showed earlier, a power line 60 hertz humming noise. And it can also, if you're dealing with variable frequency drives, it can also occur as high frequency oscillations. So you could really see this as switching noise when you're making the measurements. The second problem that it can cause is high energy transients. We talked about the case where the lightning strike causes the ground potential to jump up several hundred or several thousand volts, and these transients will want to clear through the circuit ground instead of the earth ground. So what's going to end up happening is it's going to run through your instrument and your device as opposed to running through the receptacle or the earth ground, which you would expect, but in this case, it's going to damage your equipment. And the third way, which is not commonly thought of, is ground loops can really cause common mode noise. And this occurs between not only the phase, neutral, and ground in the power distribution system, but it can also cause common mode noise in the internal circuitry as well. So this is internal circuitry of your data acquisition device, okay? And the phase, neutral, and ground, that could be either the computer or the device under test. So this noise can really be injected into power supplies, and it can also pass on to the electrical components. And this noise will not only affect your measurement accuracy, but it has the potential to become a overvoltage condition. So let's take a look at ground loops. Let's illustrate the problem so we can really understand how these situations can occur. So to illustrate the concept, take, for example, the picture on the left where we have the terminal station in one room, and then so this terminal station could be a test cell, for example. It could be a motor. It could be a switch mode power supply. Basically, it could be any sort of test system that you have, for example. And in the other room, you have a computer or a test stand. And what happens is if you connect the two stations to the power receptacle and you run a communications cable between the two, you've now created a ground loop. So the way to eliminate ground problems, if you can, is to take a look at the illustration on the right. And the illustration on the right demonstrates a system where everything is referenced to one control point, so one common point. So in that example, we have two enclosures with two isolation transformers. The isolation transformers can be going off to two different or two same power mains. And in those examples, you have not only a local reference point within the enclosure itself that's isolating each system, but you also have a dedicated control system ground. And this is dedicated to maybe a plant control ground, but in essence, what you want to do is make sure that all the grounding occurs to one specific point. And this will really prevent any sort of transient voltages or any noise being injected from one system to another. So as you can see, even though we have a I/O signal from enclosure 1 to enclosure 2, this does not result in a ground loop. And this is really because each of them have a isolated return. So what that means is the output and the input from both sides are not referenced to a different ground. But let's say, you know, and this commonly occurs in many facilities, let's say it's not practical to connect everything to one local ground. And in those situations, a common solution is to not only implement isolation, but signal conditioning as well. And we'll take a look at what are the different types of isolators and signal conditioners you can use to really solve those problems in the next section. But for now, let's move on to our next problem. So crosstalk is another issue that can occur because you have a ground loop. And crosstalk occurs when you have noise from one channel. Let's say you have a multi-channel data acquisition system. You have noise from one channel that carries over to the next channel. So we're defining this as crosstalk is the interaction between readings on two or more channels. And this is a pretty common occurrence for data acquisition systems today that implement multiplexing technology. So this is channels are switching from one to the next, and they're all being controlled by the same analog to digital converter. And what happens is the multiplexer's inputs have a capacitance that stores a certain amount of voltage charge, and that's directly related to the impedance at each signal source. So it takes some time for the voltage to really bleed off, and if you're dealing in situations where you have high frequency signals and you need to switch quickly from one channel to the other, there might not be enough time to bleed off the voltage and drop it back down to zero. So what you're going to see is that voltage or that noise carries over from one channel to the other. And in effect, the capacitance has less time. The faster your signal is, it has less time to bleed off its charge before it reaches the A to D conversion. And an instrument with built-in isolation amplifiers on each channel is really what's needed to solve this problem. All right. Next, we're going to go into the principle of common mode voltage and common mode noise. So common mode input voltage, it's defined as the voltage applied between the common terminals and the two input terminals, with the condition, there's a condition that the two input voltages must be identical. So in other words, the two input terminals may be connected together, and you have the situation where common mode voltage is applied between the two terminals. So as you can see, for example, you have some voltage going between the sensor, and there is a common mode voltage that occurs between the two inputs of the differential amplifier in reference to the power ground. And this can really cause permanent damage to the measurement hardware, because typically common mode voltage will run into the hundreds and thousands of voltage. And in practical test and measurement situations, you know, the common mode voltage is obviously going to exceed the instrument's amplifier input rating. That input rating is typically about 10 volts, and so it's very low. So we need to be able to isolate the common mode voltage from the instrument's internal amplifiers. And so, you know, with common mode voltages, you're going to have common mode noise, and we talked about this earlier, separating it into two categories. So on the left, you have the common mode noise, which is noise common to both terminals, and this could be, you know, your line as well as your neutral. And so when you make the measurements, you're going to have a voltage difference reference from ground. Now, in terms of differential mode noise, this is typically going to, hold on, excuse me for a second. Okay, I apologize for that. So differential mode noise is going to typically occur as the actual signal as well as the noise itself. So when you're making the measurements, you're going to be measuring the actual signal, but then you may have influence of noise onto your signal. And isolation can be used to remove this problem. So what are the common causes of common mode voltage? No pun intended. Common mode voltage can typically occur if you're making thermocouple measurements across powered devices. So this could be, for example, a industrial automation plant or a motor and drive application where, or even a battery cell testing where you're making thermocouple measurements across multiple points. And what you're going to have is some common mode voltage that occurs in between the channels. Another situation is also fuel cell testing as well as battery testing. If you're working with an external sensor power supply, or any sort of floating type measurements in a noisy EMI environment, this will typically cause you to see some common mode voltage. And as an example, let's say you have a 1-volt signal at one battery cell, and that is the reference to ground. In reference to ground, there is 0 common mode voltage. Now, let's say you have the second, the third, or even the 4th battery cell where you're trying to measure that 1-volt signal. What's going to happen is, because there's common mode voltage in between that cell in reference to ground, you're going to see that the actual measurement is going to be 1 volt plus that 399 volt common mode signal, and that's going to result in a 400 volt measurement. Well, obviously, you know, you're looking for a 1 volt measurement, and that's not correct. So how you can tell what common mode noise looks like, as you can see at the very top, we have the original signal with no common mode noise, okay? And really what I'm trying to show here is if the effect that measuring with different devices will have on the accuracy of your signal. So if you're using a device that measures if you're using a pseudo-differential device to measure the battery cell or the fuel cell and you have no common mode noise, what's going to end up happening is the signal's not going to be recreated accurately because there's going to be influence of common mode voltage. But if you measure the signal using an isolated digitizer, you're going to see that it's going to accurately recreate the original signal with no common mode noise. Now, I want to get into another specification that is not commonly thought of, and it's often an overlooked specification. Now, I'm an avid professional football fan, so to give you an analogy, when I'm watching a football game on Sunday at my house and I have my girlfriend over, oftentimes I get interrupted by the common noise of my girlfriend asking me to do various tasks around the house. Now, I have an ability to reject this noise and only focus on the signal that matters, which is the game. So how much of the girlfriend's noise comes through, and my ability to interrupt that is what you can think of when you are looking at common mode rejection ratio. So in essence, common mode rejection ratio measures how much input offset voltage changes as the common mode voltage changes. So giving you that fuel cell example, you know, with the second and third where fuel cell where you have that common mode voltage, if that changes, it's going to introduce some offset voltage change as well. Now, manufacturers typically represent the CMRR in decibels, and, you know, to really simplify how we can apply this, I've listed out here typical specs and how it occurs, or how it affects your noise rejection and your ability to filter out that noise. So you can see at the very top, 40 dB common mode rejection ratio is very poor for rejecting noise. You're going to be measuring the signal with a lot of oscillating noise. And at the other end of the spectrum, if you have 100 dB or greater CMRR specification, that's really world-class noise rejection that you're going to pay a lot of money for very high accuracy and sensitive measurements. So you would want to consider, you know, the 100 decibels of common mode rejection ratio if you are trying to measure microvolts or nanovolts even in the presence of maybe, let's say, hundreds or thousands of common mode voltage. So we've been talking about all these problems, and you know, in the situation where you're not able to modify the system wiring because you know, it's too expensive to go in and install a control point ground as that industrial system plant example I showed you. A really cost-effective way of solving the issues of common mode noise, ground loops, crosstalk, and even unwanted noise is implementing an external isolation barrier. Now, obviously, if you're working with a system design and you're able to implement internal isolation, that's going to be beneficial as well because it is the more cost-effective solution. But really, the main point of this isolation barrier is to interrupt that ground loop circuit. So it prevents current from flowing between your device and your instrument. And by breaking that ground loop, you negate the common mode noise as well as any other unwanted noise. And there are other added benefits as well. It's safe, so that if a transient occurs in your system and it does happen to flow through the device, it will not transfer over to the instrument. And if your user is operating the instrument at the same time, it's not going to harm him. The other thing it's going to do is it's going to help you to reject unwanted voltages or any offset voltage that can affect the measurement accuracy. So this is installing an isolator or external isolation is really one of the easiest ways to eliminate ground loop and ground loop problems. So let's talk about one of the oldest technologies out there. Common type of galvanic isolation used in early design was the analog isolation amplifier, and it was used to isolate the sensor circuit on the factory floor from the signal processing system in the control room. And isolation amplifiers also protect the data acquisition components from potentially destructive voltage present at remote sensor systems. So these amplifiers, these isolation amplifiers are incredibly useful if you need to amplify also low-level signal changes in a multi-channel application. So isolation amplifiers, if you recall in the crosstalk example, if you install an isolation amplifier at each channel, you're going to prevent the voltage from bleeding into the next channel. And one other benefit that analog isolation gives you is the ability to protect the A to D converter in your measurement system. It's arguably one of the most expensive part of the data acquisition device itself. And what you're doing essentially is you're creating a isolation barrier. So your input signal goes into the attenuator that may amplify or change the gain of the signal. And that signal will be passed on to the isolation amplifier. And at that point, you have an isolation barrier that protects the A to D converter as well as the ASIC in your data acquisition. And so this is, you're going to protect your system, and it's going to also allow you to, again, measure the small signal changes in the presence of high common mode voltage. So, for example, we talked about earlier in the example on the left, you're trying to measure the 50 millivolt change in the presence of 200 volt DC common mode voltage. So the key thing to remember when you're choosing isolation amplifiers, these analog amplifiers, there are two key specifications you should take care to consider. The very first one is the isolation breakdown voltage, and this defines how much common mode voltage the amplifier will tolerate before it becomes damaged. And as we talked about earlier, the second specification to take care of is the common mode rejection ratio, and that defines the degree to which the common mode voltage will disrupt the normal measurement. So we talked about the isolation amplifier being applied to each channel, and to minimize the crosstalk, if the data acquisition system itself has not only each separate isolation amplifier, but maybe potentially also separate ADD converters for each channel, that's going to benefit you for high-frequency signals. And what you want to do is provide a low impedance path for the signals at each channel. That low impedance path will allow the stored energy to quickly discharge before it reaches the ADD converter and reports its value. The other thing that can eliminate crosstalk is if you place metallic shields around the equipment or around each input channel, or if you provide metallic shields in the cabling itself, in the test leads. That's going to prevent the noise from entering into or leaving each channel. So let's talk about optical isolation. Optical isolation, fairly simply, uses an LED to transmit the signal across an isolation barrier. So basically, you are passing a current that will cause the LED to produce a light, and as that light is exposed to the photodiode, it will receive and convert that light back into a current or the original signal. And optical isolation is the most commonly used method to couple digital signals. So in today's world, where we have variable frequency drives and we have PWM signals, optical isolation is the preferred method because it does give you the benefit of high-speed data transmission. And not only that, but it's a true isolation barrier. So it's going to give you the advantage of being immune to both electrical and magnetic interference. And the other great thing about it, too, is the voltage barrier that you're implementing can have isolation up to the thousands of volts, whereas some of the other isolation techniques may only provide a couple hundred volts of isolation. Capacitive isolation is based on an electric field that changes with the level of charge in the capacitor plate. So the charge is detected across an isolation barrier, and it's proportional to the level of or the amplitude of the measured signal. So the capacitor or capacitive isolation, it's a passive device that doesn't require any external power source. So for this reason, it's a very simple design, and it's a very cost-effective solution for passing the signal between the source and the receiver. And it's great for signal bandwidth up to 50 kilohertz. Anything above that, you may want to consider using optical or a different form of isolation. But because capacitive isolation uses electric fields, it does become susceptible to interference from external electrical fields. But it does provide you with good noise immunity to magnetic interference. Inductive or magnetic type isolation uses a pair of coils separated by a layer of insulation, and this insulation provides the isolation or the physical signal separation. So you have an AC power source that's connected to the primary, and by varying the current, you create a magnetic field, and you have on the secondary an induced voltage where that induced voltage is proportional to the primary current. So Inductive isolation is good for also high-speed transmissions if you're dealing with 100 kilohertz or higher. But the main thing to be careful of is because it uses magnetic field for data transmissions, you can experience interference from devices that produce an external magnetic field. The other great thing about inductive isolators, they provide high CMRR performance, and it can sustain itself in the presence of high common mode voltage. Okay, the last one, not all AC powered devices are generated from or powered by AC line power. So really, we have a need for external isolators as well. And isolation transformers are also a good method for detecting low voltage signals that are riding across a high common mode voltage. And external isolation devices can be used to safely separate the device from the power mains, as well as separate the device from the measuring instrument. And it can also provide you the benefit of providing a power source to the motor device or whatever it may be that you're connecting to. Now, the next isolation that we want to talk about is digital isolation. And digital isolation is typically placed after the analog signal is converted to a digital signal. And as we mentioned earlier, ADD converters are one of the key components to any analog data acquisition device. And for the best performance, the input signal should be as close to the ADD as possible. And this is really to reduce the amount of errors that can occur from gain, non-linearity, or any offset introduced as the signal goes from the attenuator to the ADD converter. So by placing the ADD converter closer to the attenuator, we get more accurate measurements. And one of the common misconceptions in the past was that digital isolation was expensive and not as flexible, but that's really not the case. Technology has come a long way now, and digital isolation provides you better performance for any signals above 100 kilohertz, and it provides high performance or high accuracy for high frequency signals. So digital isolators are now the preferred method for any PWM signals, variable frequency drives, or any sort of oscillating RF signals as well. So with all these isolation amplifiers, analog and digital, the next thing we want to talk about is probing and signal conditioning when we're connecting our data acquisition device to the instrument. Now, in the old days, one of the most unsafe practice that was introduced was floating the instrument. And the idea behind this was there was a need to measure floating signals, and at that time, differential probes were expensive. So engineers had this idea of not grounding the instrument. So as you recall, data acquisition devices, if you look at the power cord, it is three-pronged. Some engineers were using two-pronged power cords to power the instrument, and this is really unsafe practice because many data acquisition devices have metal chassis. So if you float the instrument, what ends up happening is there's a voltage potential between the instrument in reference to earth ground, and that voltage difference can be hundreds or thousands of volts, and anywhere, any exposed metal or any accessible parts is going to carry that high voltage So if you as an operator, you're touching that instrument and you power it on, that's, a couple thousand volts that's going to be running through your body, which is definitely an unsafe practice. But also, this can occur if you're connected to a cabinet or an enclosure as well. So one of the easier solutions or popular solutions that they implemented was the A minus B solution. So taking two passive voltage probes, both probes are referenced to the same ground point, and you have the probe that's measuring the voltage difference across one point of the circuit, and then you have the B probe, which is measuring another voltage across a different point in the circuit. And what you're trying to do is you're trying to measure the voltage difference across A to B. And this A to B technique was a simple method. Sometimes it got the job done, but it did not work well when there was high common mode voltage. And this is the case because when the common mode voltage is greater than differential voltage, you're not going to be able to detect that change, okay? So both voltages are going to be reading the same if you have a very high common mode voltage and you're trying to measure a low differential voltage. You also have to remember that this technique is a math calculated measurement, so it's not a true measurement, and you're not going to get the guaranteed accuracy that you're looking for. So in those situations, obviously differential probes were now used to measure the potential difference across point A and point B. And differential probes were, good for the performance. They had a very high common mode voltage specification and very good CMRR performance as well. But, these devices are typically powered by a battery or by an external power supply. So this is added cost that you have to consider. And the thing about it, too, is that there's still a path for the voltage to leak back into the instrument. And when this occurs, this is going to come up as noise in your signal. So this is more so in the case where you're dealing with high-frequency signals, and you have these transients that will affect and that will leak through from the voltage probe to the instrument itself. And, if you're using a non-isolated instrument, you're going to have this problem. So the solution to this was to implement an isolated system. And the isolated system provides you with true and complete isolation so that no leakage current or no leakage voltage will affect the measurement itself. And isolation can mean either channel-to-channel or channel-to-earth isolation. So the obvious benefit of having a true isolation method in these data acquisition devices is that you can measure multiple signals referenced across many different voltages. So when it comes to cables and connectors, some safe practices that you should always promote: avoid metal contacts, always use shielded or insulated parts, and make sure when you select the insulation, make sure it's approved for high voltage. Also, if you're dealing with crosstalk issues, make sure you use a shielded cable pair. And, it's tempting to run all your wiring through one conduit, but the simple advice for that is don't do it. It opens up troubles for magnetic coupling or induced voltages caused when you have the cables too close to each other. Now, let's say you want to use differential probes. What do you need to consider when you're choosing differential probes? The first thing is considering the overvoltage category. So IEC 61010 defines 4 different categories for voltage measuring devices. So, for example, category 4 is for when you're measuring across a source at a low voltage installation. So this is less than 1,000 volts. So this is your power source. This is less than 1,000 volts. On the flip side, category 1 is when you're making benchtop circuit measurements that are not directly connected to a main power. So that's 120 volts or 240 or 480. The other considerations you need to consider is definitely the maximum floating voltage, the attenuation that it provides, so that you can use the full amplitude range, as well as the common mode rejection ratio, you know, that ability to deflect the noise, okay? So let's go into some isolation architectures in today's data acquisition. Many built-in isolation systems implement 4 different architectures. So the very first one, you have channel-to-ground isolation. The second one, you have module-to-module isolation. The third one, you have channel-to-channel isolation. And the fourth one, you have over-voltage protection, or maximum withstand voltage. So the channel-to-earth isolation provides you with the benefit that all accessible parts on the instruments are safe from high voltages. So if you touch the chassis of the instrument, you're not going to harm yourself. And the other benefit that it also provides is it prevents you from creating a ground loop and for causing common mode noise. So typically what you'll find is modular data acquisition systems where there's an isolation barrier from the analog module to the backplane of the instrument. And that's what gives you the channel-to-earth isolation. The next one is module-to-module isolation. This is great for keeping each of the modules isolated from each other. Many of you are familiar with plug-and-play type modular instruments. And this is provided so that you're making all these different types of measurements, whether they be voltage, temperature, strain, or pressure. These measurements will be not affected from each other when it comes to noise or any transient voltage. The third type is channel-to-channel isolation. And again, this protects you from crosstalk, so noise bleeding from channel to channel. It also prevents high energy transients from damaging the entire module. So let's say you expose channel 1 to too much voltage. Well, your channel 2 is going to be protected, and you will still find that it's accessible to make measurements. So when it comes to choosing the right data acquisition instrument, what you should be careful or consider is, first of all, the isolation architecture. Does it implement these 3 things: channel-to-channel, channel-to-ground, and module-to-module isolation? And this is going to provide you with the best noise immunity and the most accurate measurements. The other specifications that you need to take care of, maximum continuous input voltage is the maximum voltage that can be measured across all inputs continuously. Now this can be different from maximum direct input voltage because direct is when you do not have any sort of voltage sensors in place. So 2 different specifications. Maximum common mode voltage, as we saw, if you have too much common mode voltage, that can damage the internal components of the instrument. So make sure the specifications of common mode voltage is high enough for the situations that you're dealing with. Maximum instantaneous voltage is for the case where you're dealing with very high transient voltages. So if you run the risk of lightning strikes, you want to make sure that the specification will run into hundreds of thousands of volts to protect your instrument and your user. And last one, the maximum withstand voltage. This is the maximum voltage that the insulation material can handle before the barrier starts to break down. So typically the isolation barrier is some sort of insulation material. If you apply too much voltage, that can start to affect the performance of the installation as well. So I just want to quickly cap off with one of the ways Yokogawa implements our technology in terms of isolation. What I have here is our modular scope quarter DL850E series. It's a modular system that implements a combination of optical and digital isolation. And what this allows you to do is you can have up to 16 channels of very high speed, 100 megasamples per second sampling speed per channel. And it gives you very good resolution as well. So you have not only 12-bit A to D resolution, but even in certain cases you have up to 16-bit resolution. And to put that into perspective, 16-bit resolution is approximately 5 to 6 significant digits. So this is what you would find on very high accurate systems, power analyzers as well. It has a complete built-in isolation system, so it implements the three that we talked about, which is channel-to-channel isolation, channel-to-ground isolation, as well as module-to-module isolation. And what this means, put here as an example, let's say you're making a pulse measurement, a PWM, or a VFD measurement, right? And if you're using, for example, 10 megasample per second module, so even though that's high speed, if your signal is too fast, you're not going to be able to accurately recreate the signal. And what you end up having is this stair-stepping effect, which I'm sure most of you are familiar with. But also when you're making the high voltage measurements, it's not going to be able to accurately capture that spike, maybe that you have an inrush voltage or an inrush current, and you're not going to be able to accurately detect the peak. So really you need high-speed sampling to be able to accurately sample enough of the signal to recreate it. And lastly, we also have a PC-based data acquisition device. So this is the SL1000 series. This fits perfectly well into automated test systems, fully compatible with LabVIEW and MATLAB devices. So this is very good for if you're running an automated system and you don't want to run the risk of harming the user, or maybe you have a test cell environment where the user cannot easily access the instrument. So this is another one of the solutions that we have for measuring high voltages at high speeds without running the risk of being exposed to these high voltages. So at this time, this concludes our webinar. I will pass it over to Christina for some more housekeeping items. Thank you all very much for your time.
Thank you, William, for your presentation. Unfortunately, we have run out of time for our Q&A session, but please be assured that if you submitted questions via the chat, they will be answered in email. And remember, you can always reach out to us at webinarwednesdays@us.yokogawa.com. With that, I'd like to once again thank you for attending and participating in our webinar. When you do close this webinar, please take a few minutes to fill out our brief survey that you will automatically be directed to. Once again, thank you and have a great day.